Yeah, so this is kind of a crazy read. Yeah, so there's this, you've probably heard of DreamBooth before, but there's a paper that came out 2 days ago talking about HyperDreamBooth, and HyperDreamBooth is supposed to do what DreamBooth does with one image. And I mean, this paper is a little deceptive in how it does it, but it also introduces some really interesting stuff. So I do just want to say that the paper is, I mean, the paper is difficult to read. It feels a bit rushed to me. Um, and it doesn't seem that dense, but there's not a lot of explanation there. Um, but it also it feels to be a little deceptive in what it advertises what versus how it does that. So, anyways, I mean, let's get into it. So, uh, what is the goal? So the goal is if I have this diffusion model. So I have this diffusion model that I've already trained, say Stable Diffusion 1.5, which I think is what they use here. And Stable Diffusion 1.5 is, if you haven't seen diffusion model, or if you don't really know how diffusion models work, then I've made a video on that, so I would check that out before this. But Stable Diffusion, it basically generates images from text using Gaussian noise. And what we want is we want to kind of fine tune Stable Diffusion to generate different styles of this image. So you can see we have this picture of this guy, and we put the picture, this one picture, through this hyper network, and then the text to image model, which is the Stable Diffusion model. So this is the Stable Diffusion model, and you give it the text. So AV. So V is a special kind of word that's going to be used. We'll get into that. So there's a lot of moving parts. And then you say, so this face as something. So in this case, it would be this face as, say, Barkskin, or this face as, say, Rockstar. And the way you do that is using this DreamBooth method that they propose. So yeah, at a high level overview, that's what we're doing. We're taking this image, we're going to throw it through this network here, and this network is going to output something which we're going to use to change Stable Diffusion a little bit. And by changing Stable Diffusion a little bit, instead of it outputting anything from the Stable Diffusion distribution, which is literally anything, it'll only output certain styles of the image we give it. And specifically, they work with faces. I don't think they do anything else but faces in this work. I hope. I mean, it'll probably generalize to other modalities, but it looks like they only work with faces. But yeah, so that's a high-level overview of how this works. Now, so if you haven't seen my Stable Diffusion video, or if you haven't seen someone's Stable Diffusion video, if you don't know how that works, then I would go and check that out. And also LoRa as well. Also going to be looking at LoRa a little bit, so I would go and check out what LoRa is as well, because I'm not going to specifically go too much into detail over either of those. But nice thing is we get an improvement on Best Girl LoRa. So good old LoRa. They do a improvement on LoRa, and the way they do the improvement is very confusing. But I think I finally understand how they do it and why they do it. So we know how LoRa works. So if you have this feed forward network, so you have this vector x. X is in this case it would be, say, we'll just do r of 1 by n. So the sequence length is 1. It just makes it easy, so it's just a vector. and then you'll multiply this by a weight matrix. And this weight matrix is this weight matrix is already, it's not fine-tuned, this weight matrix is already trained. So this is in your stable diffusion model. You have this linear layer where it's a weight matrix in R of n by R, or n by m, and then the output will be a vector of shape m. So you'll get this vector, which is, say, z sub 1. We'll call it z sub 1. And to mark this as frozen. So this was trained by the original model, and what you do is you freeze this layer, and you're going to fine-tune this layer, and you use a LoRa, or you want to fine-tune the whole model on something, whatever you want to fine-tune this stable diffusion model on. So if you want to fine-tune it to produce faces, then you would fine-tune this model on face data. And you would freeze that data, and instead of fine-tuning this, you would instead fine-tune this adapter module, which we have. These are the LoRa matrices, and you create two matrices, A and B, where A is in R of n by R. So yeah, n by R. And then B is in R of R by M. And then the output matrix, or the output vector, will be Z2, which is where both of these, Z is in R of 1 by M. So you just kind of use two of these matrices, and the reason you use two of these matrices is because the total number of parameters here is going to be less than the full rank parameter here. If you add up the number of parameters, if R is kind of small, then you'll get less parameters, and you can use an R of 1. So the number of parameters here would be n plus m, and the number of parameters in your original weight matrix is n times m. So you can clearly see there's a big difference there. And just to finish this, you add these together to get your final z. So z, I guess your output y is equal to z1 plus z2. So that's your output. Now, this is normal LoRa. And what they do is they introduce a new method, and they kind of decompose A and B into two more matrices. And they they basically want to make this smaller, these matrices here. So the way they do that is by, let me get my highlighter. So the way they do that is by creating these. So if we just look at A, you can see there's two matrices here. And A is decomposed into two matrices. So A is the original LoRa matrix, which we want to use for fine-tuning. But if they want to make it smaller, then you decompose the LoRa matrix into two matrices, AUX and A-train, where AUX is in R of n by A, and A-train is in R of A by R. So in this case, if we say n, n is whatever, maybe that's 512. A is 100 in their case, and R is equal to 1 in their case as well. So you'll have this matrix here, or you'll have this vector here. So this is your x vector, and this is in R of 1 by n. And then you multiply that. So you take the dot product with this other matrix, which will be, so the first matrix, which is AUX, will be a matrix of shape n by R. So this will be a matrix of shape 512 by, A by n by A, which is 512 by 100. And then you have the second matrix, which will be maybe a little bit smaller, which is going to be A by R. So this will be A by R. Now you can see if you multiply these two matrices together, you get your original matrix A in R by N by R. So that's the original LoRa matrix shape. And you decomposed it into two matrices, where this matrix is a lot bigger and this matrix is a lot smaller. Now, they say the aux layers are randomly initialized with row-wise orthogonal vectors and are frozen. So if we look up here, you can see we decompose the A matrix into two matrices, and then we decompose the B matrix into two matrices in the same way you did the A matrix. So you have this N by A, and then you have A by R, and then you have R by B, and B by M. And if you multiply all these together, or if you multiply A aux by A train together, you'll get the original LoRa A shape, and if you multiply these two together, you get the original LoRa B shape together, or you get the original LoRa B shape. Now, this obviously isn't going to give you less parameters if you just do this normally. So I have this example up here where, let's say A is 256, we have these over here. So let's say N is 256, R is 1, A is 100, and B is 50. So these are all the parameters they use except for N. So N is our embedding size. That's 256. Now if we multiply out the parameters, we get a total number of parameters of 38,000, which is clearly a lot. And that's way more than the original LoRa, where the original LoRa would be 256 times 2, so it'd just be 512. So that's a lot more. And in this case, N is equal to M as well. So I'm just making it a square matrix to make it easy. Now, to reduce this, what they do is they introduce this matrix here, which is the row-wise orthogonal vectors. Now, you may be thinking to yourself, wait a sec, this is not a square matrix. How the heck am I going to make this orthogonal? Now, there exists this thing called a semi-orthogonal matrix. Now, the definition of a semi-orthogonal matrix is if you have a matrix A, so this is our semi-orthogonal matrix, then by definition, this matrix is semi-orthogonal if A dot AT is equal to the identity, or AT dot A is equal to the identity. Now, this matrix here, it can be rectangular. You can have a matrix that satisfies these properties that is rectangular. So that's what they do here. They create a rectangular matrix that satisfies these properties here. Now, how the heck are you going to make this matrix? So I played around with this a little bit, and I found a way to kind of create this using Python. So if we have a matrix n by a, and in this case, in my Python example, I set n is equal to 3 and a is equal to 2. Now to do this, there's this library called SciPy, so you probably used it before. Now using SciPy, there's this function called ortho group dot RVS. Now you can create a 3x3 orthogonal matrix by this function here, or you call the function with a 3, and that creates a square matrix. And then you can kind of slice the matrix to that. So you slice it to 2, and now you have this rectangular matrix, which it'll kind of look like this, and it'll have, so it'll be your 3x2 matrix. Now I have an example here which satisfies this property. So if I do 0.28, so 0.28, 0.76, negative 0.55, negative 0.36, and 0.78, and negative 0.54. Now if you multiply this, so if you do that times its transpose, or the transpose of that times itself, if you do the transpose of this times itself, so if we call this A, so this is A, and if you do A transpose by A, you get your you get a 2 by 2 matrix that is orthogonal. Now, this isn't, so the reason you use this matrix is because if you multiply anything on the left or on the right side of this matrix, so if you do AX, then one of the nice properties of this is the norm of this is equal to the norm of the input vector. So this satisfies a nice property where the transformation it retains the dot product while you or it retains the magnitude of the vector. So it's kind of like a rotation in space in a way, which is kind of weird to think about because the vector itself would have moved. So the vector itself would have moved from a two-dimensional space to a three-dimensional space, and you do this rotation in this way. So it satisfies this nice property where it retains its magnitude in space. Now, if we're doing anything with this matrix here, you may notice that like this A matrix, so if we have, so this is our N, this would be this first matrix here, my highlighter, it would be this first matrix here. Now if we multiply anything on the right side, that's not going to be very useful because that would bring us, like we're not doing anything with A. But if you multiply, so whenever you say combine these matrices together, then you're going to be multiplying by this matrix here, by this this A by R matrix. So let's just say we have a matrix AOX, which is in R of 3 by 2. So N is equal to 3 and A is equal to 2. And let's assume that it satisfies the property that we defined up here. So it satisfies this property here, and it also satisfies the property where if you multiply something by this matrix, then, or on the right side, this property here, or if you multiply it by a vector on the right side or a matrix on the right side, it retains the magnitude of the vectors. Now, we also need to have that matrix will be defined by a train. That's the second matrix here, is going to be an R of 2 by 1. So A is equal to 2, R is equal to 1. Now if we do AOX dot A train, then that results in A, so that will result in A in R of 3 by 1, which would be our LoRa matrix. And if you noticed, since it satisfies this property here, and we multiplied A train on the right, then A train, so even though A train is this really small matrix, whenever we multiply it by AOX, since AOX is this semi-orthogonal matrix, it will retain the dot product of all the it'll retain the magnitude of all the vectors in A train, meaning that you maintain a lot of the properties of A train, and it doesn't really change A train in any like meaningful way. So it retains all the nice properties of A train. So it kind of maintains A train, and even though A train has a lot less parameters than you would. So it's kind of like whenever you multiply it on the right side, it maintains the properties of A train. Now, as an example, so I have this matrix here. If I had this matrix here, which I defined earlier, that was orthogonal. It was 0.28, negative 0.55, 0.77, 0.76, negative 0.36, and negative 0.54. So this is AOX. Now if A train is, so A train is going to be 2 by 1. Now that would look something like this. So it'd be 2 by 1, and if I do 1, 2, and you multiply these together, then this will result, so that'll result in a matrix that is 3 by 1, obviously, and the matrix that is 3 by 1 will be 1.8, negative 1.3, and negative 0.3, about. Now the magnitude of this is about equal to the magnitude of this here. So yeah, if you write it out, then the magnitudes here will be 2.23. Yeah, 2.23 about. So I think that's the magnitude. Yes, I think that's right. Yeah, 2.23. Okay, sorry. Yeah. So if you take the magnitude of the output of the two matrices and the original, then you have this very nice property. And notice that the number of parameters here is one less than you have here, and this grows with scale. So if you have a lot, like if you grow these matrices a lot, then the number of parameters in this matrix will be way less than the number of parameters in the original A matrix. And notice how I called that train? Well, that's kind of a hint that we're going to train this thing. So you can see that we have, so with all that, all that, all those properties, you can see that we have this matrix here that we're going to train that is a lot smaller than your original A matrix. But since you have this matrix, this semi-orthogonal matrix here, that you can multiply, or that you can take the dot product of with this, with the A matrix here whenever you're done with it, then you don't really lose any. You don't really lose anything by making the matrix smaller because you have this orthogonal, this semi-orthogonal matrix here. Now, I think that's what they were saying here. It's kind of difficult to read and get that out, but I'm pretty sure that's what they were saying, where you create these orthogonal matrices, the A and B separately, and then since they have the property here, since they have this property where in this case B would be the transpose of that. So, but since they have these properties, then you don't lose any information by making the A and B train matrices smaller, where that's train and that's train and that's aux and that's aux. So I hope that makes sense why they do that. So you basically so this is the part you're going to be training here, and these are the parts you're going to be freezing here. So I hope that makes sense. And if not, then basically you're just making the LoRa matrices smaller, so you have a lot less parameters that you're training, meaning that you have a lot less things that you have to store in memory because of Atom and your optimizers. So there's a lot less you have to store in memory, and that's the whole point of LoRa. And making it even smaller is even better. So we make it even smaller, and since these are frozen here, you don't have to worry too much about them. You just kind of leave them in memory. Yeah, so that is what they call lightweight DreamBooth, LiDB. Okay, so that's the first part. That's the first thing we got to get out of the way. Now, the second thing they do is don't think about training. Yeah, so all this is for a diffusion model. Now, we're not going to be training this diffusion model from scratch. We're obviously going to be fine-tuning it, and this is going to be how we fine-tune it, just like a normal LoRa layer. So we're not going to be using LoRa layers anymore. We're going to be using these layers as opposed to the LoRa layers. And you may be thinking, where do these parameters come from? Like in a diffusion model, you usually have, say, your image, which is your noise, and then you throw this through a convolutional neural network, or a convolution, and then you throw this through another convolution, and then you create this UNet, which will output the noise, and this was your input this was your input image with noise, and that's what you would normally do in a diffusion model. But you actually, so if you look back at stable diffusion, there's these matrices, or there's these matrices that you use, the cross-attention matrices, and the cross-attention matrices are themselves linear layers because they're attention. So that's what you're actually tuning. And I think they say that here somewhere. I'm not sure where, but yeah, you're basically fine-tuning the cross-attention layers. You're not doing anything with the convolutions, and the cross-attention layers are where the other, like where you input the text modality and stuff like that. So, and that's where the linear layers are. And since they're linear layers, they're easy to fine-tune because of the LoRa properties, and now because of the lightweight DreamBooth properties. So before we directly fine-tune stable diffusion, like on the image we want, this is kind of where I say they're kind of cheating, and it's kind of not what they say it is. But what they do before is they train this network called a hypernetwork. And this hypernetwork, what it does is it takes, so you need to train this hypernetwork on a bunch of images. How many images? They say down here that 15,000 identities, so 15,000 different images to train this hypernetwork. And you may be thinking, wait a sec, didn't you say we were going to fine-tune this thing on one image? I did say that, and they also said that. So that, I mean, that's kind of the way I say they're cheating, but go with me for now. What we do is we train this hypernetwork on this large data set of images. So that could be like the celebrity data set, Celeb A, I think, or whatever the data set is called. And this is how you train this. So you have this visual transformer encoder, and so you send the images through this visual transformer encoder, and you get out this vector describing the face here. Now, what you do is you take this face vector and you append it to a bunch of weights, or you append it to a bunch of other tokens, and in this case the tokens are zeros. So you'll have this face vector here, which will be some values, maybe 0.1, 0.2, negative 0.9, and then you have these other tokens here, 0.0, 0.0, 0.0, and so on. And you have a bunch of these vectors. Now, you send these vectors, so the zero vectors, along with the face vector, through this transformer decoder. And specifically, it's a 2-layer decoder. And you send it through the decoder, but the output of the decoder is then added to the input and then sent back in the decoder. And you can kind of think of this as a residual connection here. So you can think of this here as a residual connection between transformer layers, but instead of the next transformer layer being a different transformer block, it's going to be the same transformer block. So in a way, this is like a recurrent neural network, kind of, with residuals, so it's kind of a weird thing. And maybe you can think of this as correcting itself. So it outputs something, and then that something goes back in the network, and then it goes when it goes through the network a second time, it kind of corrects what it messed up on the first time. So maybe there was some error in the first output, and then whenever you put it back through the network, it kind of corrects that error. Now, what do we do with these matrices? Well, you can see there's no face matrix here, or there's no face vector here. And these vectors here, the outputs, are sent through a linear layer, so this may be in some embedding space, E. And remember, the matrices we want are A by R, and R by B. So that's A by 1 and 1 by B. And if you look at these here, we can send this through a linear layer. So this linear layer may be E by A, and then this linear layer may be E by B. Now, whenever you send it through these linear layers, you'll get out a bunch of vectors, and say the first vector, since the matrix was E by A, then you'll get out a vector that is of shape A. And then this last vector, say since that's E by B, you would get a vector that's of shape B. So these output vectors here are going to be your weights, your direct weights for the LoRa layers. Now, why do we do this? So if you look at original LoRa, these are fully connected layers, meaning that there is no way to change them. Once you have this fully connected layer, it is static. There is no way to change it. And the nice thing about attention is you have this dynamic routing of information. Now, if you do this, if you use this HyperNetwork here, then depending on whatever your image is, the LoRa weights are going to change, it's very interesting because if you just fine tune on LoRa normally, it may overfit to what your task is, or it may not be that optimal for whatever your task is. Maybe it doesn't have enough representation power or something like that. But if you have dynamic LoRa matrices, there's a lot more representation power to that. And that's what this HyperNetwork does. And you train this thing on whatever downstream task you're doing. And remember, we're doing faces. So you train this thing on faces. And the HyperNetwork, it'll take in a single image and it'll output all the LoRa weights for that image. And you keep the entire Stable Diffusion network static, and you only change these layers here. So you have your convolutional neural network, or you have your convolutions and everything, but you only change these parameters here. So whenever you kind of fine tune this HyperNetwork here to take the output of Stable Diffusion, and instead of producing, say, I don't know, maybe a cow based off. So if we go up here, maybe if I give it this noise here, and I don't have this HyperNetwork, so say it's just this part here, and I give it this this noise, and I don't have the text here, then maybe it'll output a picture of like a dog or something like that. Maybe it'll output something something kind of random, some output. But we want faces, so we take this HyperNetwork and we train it so that instead of it outputting like a dog or a cat or something like that, the noise will instead be transformed into a face. So it'll be this face here, and the face, so you instead want it to produce images on your downstream tasks specifically. So if we were trying to produce something else, say pictures of cats, then your data set would be pictures of cats, and your outputs of the HyperNetwork would be weights for the LoRa layers in the Stable Diffusion model, which would output pictures of cats, but in this case it's people. And then they have this prompt here, which we'll get to in a little bit. So the way they train this model is by looking at the diffusion model, and they have two terms here. So this first term here is your normal reconstruction loss. So if we go back up here, you can see if I give it this first image here, then I want it to produce the same image. So it's just your reconstruction loss, so Stable Diffusion has to reconstruct the image given this noise, and this frozen Stable Diffusion model with our HyperNetwork, which outputs the weights for the LoRa layers in our, sorry, I say LoRa, I mean this libd, these libd layers. So your HyperNetwork will output the parameters for the libd layers, and then you want to output the same exact image. And that's just normal Stable Diffusion fine-tuning. And there's a second term here, which if you, there's a second term here, and this first part is the parameters you are training, and the second part here are the parameters that you already have, and you basically want it to stay as close as possible. Now, the way I think they do this is, so whenever you have your LoRa layers up here I showed, remember you have your frozen layer and you have your computed layer, and the computed layer, so you can obtain this layer here as a weight matrix, and the weight matrix, like you obviously have your four matrices for the libd layer, but you can combine the four matrices to be delta W, which is in R of n by m. And remember, your original weight matrix was an R of n by m. So what I think they do is they combine all these matrices together to get your delta W matrix, and then you compare these two and make sure they're not far apart. Now that does is it helps you retain the nice properties of your original stable diffusion model, but it also, since you're fine-tuning it for this downstream task, it still retains the kind of like creative style properties that stable diffusion has, but this fine-tuning part makes it so that it does so on faces specifically. Now, there's a third part we need whenever we're fine-tuning, or there's another part we need whenever we're fine-tuning this, and that's this conditional text part. And the way they do this conditional text is they have a special token face, and that's the text, because you need your special you need your conditional information for stable diffusion. Now, this V part, it comes from, so in the original DreamBooth paper, they say that they specifically invert the vocab to find rare words. And this V part is going to be a rare word. And since the V part is, it's kind of a rare token in the vocabulary, it kind of helps out the model. And since it's a rare token that since it's a rare token in the text, it means it's not going to have many relationships to other tokens in the text, and it doesn't really have a strong prior. But since it's not really related to much, you can leverage that property and make it have a very strong prior that allows it to kind of be disentangled from the rest of the information. Because if I had the text dog, so I guess dog wouldn't be good for this V, but if I had like a happy face, so if I had a happy face, then happy is happy's going to be a word that is seen a ton, and since happy is seen a ton, it may be entangled with other properties of images, which may output undesirable images. Maybe you give it the face you're conditioning on and outputs something just not even close to that image because of how entangled the word happy may be with something else. Maybe whatever prior that may be. So instead you give it a word like just some random word. Maybe you find a word in the vocab that is like a I don't know, period or something like that. Some weird word. And that only appears in the text ones. So you'll use this as your prior, or use this as your V, and then since it doesn't have it's not entangled with anything, you can have this really strong word in there that is easily able to be fine-tuned. And then, so that's the HyperNetwork architecture. And they say they use 2 hidden layers. And they say the transform decoder is a strong fit for this type of weight prediction task, since the output of a diffusion unit or text encoder is sequentially dependent on weights of the layers. So yeah, the decoder is going to be sequential, it's sequential, and since the weights here are themselves sequential, then this transformer is going to be very powerful for that. You can think of this weight matrix, or this first weight matrix, as being the first weight you're adapting, and then this one being the last weight you're adapting at the end of the network. So yeah, there's a sequential property there if you add positional encodings. So they say this transformer has very nice properties which they leverage. And then they talk about the iterative prediction. Now, what we have is this network which it's been fine-tuned on faces. So now what we can do is we can put a face through this HyperNetwork, and we can get out the weights that we will then put in stable diffusion to get that face out. Now, what they do is, now what we need to do is we need to we need to do what we said we were going to do at the beginning, which is take this image here and fine-tune the model on that image. And the way they do that is I'll show you up here. Yeah. So the way they do that is they take this image. So this is the image we want to fine tune on. So you take this image and you pass it through the hypernetwork. So you pass it through the hypernetwork and you get out these weights. Now what you do, so this is pretty cool. So since you have this hypernetwork that produces the weights, you kind of start in this spot. So if you just take the weights of the hypernetwork as the output, then Stable Diffusion will produce that exact same image. Now, what you need to do is add this conditional information. So what you need to do is kind of like stylize this image or kind of get Stable Diffusion in a mood to change the style of this image given different prompts. So yeah, so this is like the initial output guess of the network, and since the model already has a lot of the model already knows a lot about like text properties. So if you say a face in the style of ... then it'll output that. But yeah, so what you do is you take this image, you pass it through the hypernetwork, and you get the initial first guess. They say here, given a face image, our hypernetwork predicts an initial guess for the network weights. So you only pass this image through the hypernetwork one time, and you get out the weights for Stable Diffusion for the not LoRa weights, but the whatever their new weights are, which are then fine-tuned using the reconstruction loss to enhance fidelity. So you take the weights and then you fine-tune Stable Diffusion, or you fine-tune the weights, the initial weights, to get better fidelity output. So the model kind of understands this image better using the initial guess output weights. Now they also have more to that. Where is it? They also have more to that. So they say here, a key contribution of our work is the idea of relax ranked fine-tuning, where we relax the rank of LoRa model from R is equal to 1 to R is greater than 1 before fast fine-tuning. So if we go back up here, not all the way up there. So if we go back up here, before they take these weights and before they start fine-tuning the diffusion model, what they do is, so we have our weights, we have our, so the output of the network for one layer would be, so we have the AUX and we have BAUX, and then we have our image, and then we throw it through the hypernetwork, and that'll output A train and B train. And then we can get the weights for this layer by multiplying everything together, and they have the, just so I don't get it wrong, it's, so delta W is equal to, don't worry about that, delta W is equal to AUX, A train, B train, BAUX, and that's our delta W. So the first step is to take the weights of our hypernetwork up here. So step 1 is to get the weights from the hypernetwork. Step 2 is to combine the weights of the hypernetwork. And then step 3 is you decompose this again to say A prime is equal to, or A prime is in R of N by R, and B prime is in R of R by M. And what they do is they actually use the original LoRa, so not their version of LoRa, and they decompose this so that R does not equal 1, so R is greater than 1. So we go back down here, and they say specifically, we add the predicted hypernetwork weights to the overall weights of the model, and then perform LoRa fine-tuning with a new higher rank. So the reason you do this is that it adds more model capacity. So you get the initial predictions from the hypernetwork, you combine the weights, and then to give the model more capacity so that R is not just 1, it'll help it learn faster and it'll help it learn better. And you increase R to be, say, 2 or 3, so you still have this very low rank matrix, but you kind of help out the model by making this R a little bit larger, and then you do the fine tuning. So you don't directly take the outputs of the hypernetwork. So it wouldn't be these, it wouldn't be the direct weights, but you would then do what we did over here, which would be the combining, which I'll call it, and then you put those through the diffusion model, and then you do the fine tuning. So you do the fine tuning on these weights, not on the direct weights of the hypernetwork, so that the model has more capacity and the model can learn better. And you do the fine tuning on a few different on a few epochs, and this is this is where it comes in, where they say it takes them like 20 seconds to fine tune something or like that. Something like that. Our method achieves personalization on faces roughly in 20 seconds. Yeah, you're right. It does after you have this hypernetwork. So it takes about 20 seconds to fine tune stable diffusion on this one face here using that method. But that assumes you have a hypernetwork, which is kind of my problem with this paper. That you need this hypernetwork that's trained on the modality you want in order to fine-tune stable diffusion using a method. I'll rant more about that later. So yeah, and the way you do this is with this objective down here. This is just the reconstruction objective, where that's your input, that's your single example, and then that's your output, your diffusion model, and you train based off these LoRa layers here that you created from your hypernetwork. Yeah, and that is the method. So it's 2 steps. It's 1, you need to train this hypernetwork, and then 2, you fine-tune on the one image so that it can so Stable Diffusion kind of understands this image a little bit better. Now to do inference, which is down here, I do not know where they put it. Well, we'll just go up here to show you how they do that. And you can see, to do inference, you do a whatever this special token is, face as a, and then this is bark skin, and then this is rockstar, because Stable Diffusion knows these styles here, and since you have the LoRa, since you have the LoRa layers, you now have apply these styles to this image here. Now these LoRa layers make it where these layers make it where it's a lot faster to fine tune and a lot smaller, and you only have to store the lower layers, so it has some nice properties where things are smaller and faster because of that, just like normal LoRa. And you can kind of see here after fine tuning, so you kind of take this face, and so that's your these are the outputs of your hypernetwork, and then you kind of fine tune it to add a little bit of style. So this is your original estimate, and then your new estimate. To kind of add style. And that's the method. I didn't really like how they explained it. I don't really like it. It wasn't very good, I guess. So let's get to the results. Now you can see, this isn't even a fair comparison. They have HyperDreamBooth, but my problem is that DreamBooth was direct fine-tuning of Stable Diffusion. So DreamBooth was one step. DreamBooth was, I have Stable Diffusion, and I'm going to fine-tune Stable Diffusion. But this is 2 steps. It assumes you have the hypernetwork, and if you have this hypernetwork, then you can fine-tune Stable Diffusion. So it's not really a fair comparison to say this two-step process does better than this one-step process, because the original DreamBooth would take a few images. It would take a few images in as its reference. I think it could also take in one, but it would do so. It would directly fine-tune Stable Diffusion in 5 minutes. And remember, we need to train this HyperNetwork, and we need to train it on 15,000 identities. That's way longer than 5 minutes. So it's kind of hard for me to get behind this comparison here, where they say their method is better. Like, yeah, it's going to be better because you have this basis that makes it a lot easier for the model to kind of deal with, it's a lot easier for the model to get higher fidelity. You only train it for 20 seconds because the model has this hyper-network prior that it can use, but the original DreamBooth doesn't. Sorry, I'm ranting right now, but yeah, it's not really a fair comparison to say, oh, look, ours is better. Yeah, because you add more, you add this hyper-network prior that you add this hyper-network that you train on a lot more data. So I just feel like it's not very fair of a comparison. At least from what I read from DreamBooth, I don't think they have anything like the HyperNetwork at all. So yeah, I just don't feel like it's a fair comparison. But anyways, we can look at the nice quality of the images, of the output images. So you can see, I mean, the quality looks really good. There's this other method called textual inversion, but you can see that what you want is you want this image to be very close to the reference, or these images to be very close to the reference image, but also be kind of a different style. I mean, what is this? That's not that. It's completely different, but you can see it does really good on changing the style, but keeping the original face. So I think it's really cool. Don't get me wrong. I just think it's not a very fair comparison to make. Like, I really think this method is cool. And if we go down here, you can see if you fine tune it without the hyper module thing, then it does worse. And if you only have the hyper thing, then it does better in some cases. And yeah, if you do k is equal to 1, where I think that's one extra iteration through the hyper-network, then it does even better. And what is ours? I'm not sure what ours is, but maybe that's fine-tuning afterwards. So maybe the fine-tuning helps it even more. So yeah, that is that. And then they have some more studies down here. Societal impact is massive. This work aims to empower users with a tool to augment their creativity and ability to express themselves through creations in an intuitive manner. Oh man, oh no, are they talking about deepfakes? Let's see. Our proposed method inherits many possible concerns. Oh no, not the concerns that affect this class of image generation, including altering sensitive personal characteristics such as skin color, age, and gender, as well as reproducing unfair bias. Yeah, I mean, there's definitely going to be bias in Stable Diffusion. I just think it's so funny that they had to put this here. Yeah, anyways, sorry for ranting, kind of. I mean, the methods are really cool in this paper. I just think it's a little, they kind of, what they're comparing things to isn't direct with how, like, it isn't that clear, because they say it takes 20 seconds and it doesn't actually take 20 seconds. You need the hyper-network in order to make it take 20 seconds. And yeah, it is a lot smaller, but you need the hyper-network as well. So yeah, really cool method, just not fair comparisons. So let me know what you think about this. Yeah, that is HyperDreamBooth.